cloud. Okay. Okay, thank you. So we're starting the recording now, and I will see if I can bring up my. How's there? How's that look? A little better?
Nope, that's coming up. There we go.
Okay. Let me just move these toolbars around a little bit so I can. There we go. I can see most of it. Okay. So good evening. Certainly an honor and privilege always to present to the group tonight. We'll be looking at the constellation Ophiuchus. Usually on some of these difficult to pronounce names, I'll usually put in a little phonetic note so for me and everybody else. But you can see some of the one of the mythical presentations of Ophiuchus, and you'll see later on in my presentation a couple times we hit on it. Ophiuchus is located along the same line as most of the zodiac is. It's not, it's not a zodiac constellation. In past times, it's been considered the 13th, but formally, officially, it doesn't hold that distinction. But it is in that same area, so it's visible a good part of the year along the ecliptic, pretty much. A couple of details about the constellation. You can see, you get a rough idea of what the constellation looks like in a star field to the right there. Lies on the the celestial equator, not the ecliptic, the celestial equator. In the southeastern sky, generally in early July. So it's you'll see it at night. It rises not too late, but it comes up a little bit later in the evening. But is more prominent in the southeastern sky in early July. August, it sits south between 40 and 70 degrees. It's a rather tall constellation, so it's readily visible to the south when it hits its peak elevation in the sky. And then west southwest in October. That's typically, I'm more familiar with that because I have a much more open sky to the west for the most part. Now, this will vary for everybody, of course, but my preference is viewing it usually in the fall time when it's in the southwest and southwest, about 9 o'clock, not having to stay up fairly late. Like I say, some references the 13th zodiac constellation, the Serpent Bearer, its Greek origin. Neighboring constellations, you can see a little bit of them. Scorpius, if you can make it out, lies is below Ophiuchus. And of course, Sagittarius will lie off to the left of that. You're going to see Serpens, which is actually a two-part constellations. There's Serpens Cauda. Let's see if I can get this right. Serpens Cauda and Serpens Caput on either side of Ophiuchus. They aren't really easy to make out, but basically there are two lines. Ophiuchus, like I say, is the serpent bearer. A lot of the imagery that you'll see concerning this constellation deals with it. A person, a mythical person holding onto a snake. The head off to the right, the tail off to the left. Therefore, those two other constellations, which are not part of Ophiuchus, however, they are attached to it in some sense because of the mythological connotations. Some other surrounding constellations, Hercules, Libra, they're generally going to be, I think they're a little bit, I'm not sure exactly where they are. I'm sure, pretty sure Libra might be off to the right of it a little bit. And then Aquila probably trailing behind. Anyhow, there are no first magnitude stars in Ophiuchus. The brightest is roughly 2.08. With respect to the constellation, it's the 11th largest in size. It has four, I'll call them rather minor, I think, associated meteor showers. And I certainly invite, if anybody's got some additional information as we hit this points, don't hesitate to pipe in. I don't mind if you break in with some additional information. Generally, the constellation can be seen between latitudes plus 80, minus 80, so it's visible to a good portion of the globe. There are 13 named stars in the constellation, 7 stars with known exoplanets, and there are 7 Messier objects. Constellation history, like I say here again, associated with Greek mythology, associated with, there you go, Asclepius, the son of Apollo, may have descended from ancient Babylonian constellation honoring the god Nera. Like a lot of constellations, even the official 88 that exists today. It was cataloged by Ptolemy, pretty much. I think in its as we know today, there were probably some variations with respect to size and some of the included stars or object on its exterior or near its periphery. In Latin, it's referred to as Serpentarius Ophiuchus. Shown as a man holding a snake, like I say, serpent's caput, the head, is off to the right, basically in his left arm, and then cauda is the tail, and you can see that extending off to the left side, a little bit lower. And you can see a little bit of Scorpius underneath, and Sagittarius you can't quite make out coming in from the left lower portion. Some of the more prominent stars, and this is the one of the guides that I use a fair amount, and it's relatively easy to see. And I'm going to move around my people banner so we can see this. So one of the more prominent stars is Razelhig. It's Alpha Ophiuchi, 2.07, so it is the brightest star. And you can see that it sits basically up here, if you can see my cursor, up near the top of the constellation. To me, good part of this constellation is not directly like this. I think to a certain extent, it has more stars, but it's got a little bit of that shape like Cepheus does. It looks like a house, 2 or 3 story house with a peaked roof up near the top. That's the way I've always referred to it, basically, as far as basic shape. Peak of the roof here, down the sides of the house, and down to the base here, where you see these 3 or 4 prominent stars. But anyhow, as far as Razelhig, it's 4.4, about 49 light years from our solar system. It's a binary. White giant. You can see, put the stellar type in there at the end of this presentation. If you go back and take a look at it online, I've got the diagram showing all the stars and all their variations. It's about 2.4 times the mass of our sun, with a luminosity 25 times. And then there's the white-orange main sequence dwarf along with it. Type mass is just a little bit under our sun's mass. One of the other more prominent stars, okay, I'll use my cursor whenever I start, there we go, is Sabig, which is going to be Eta Ophiuchi, which is down here in the lower left. Its apparent magnitude is about 2.5, 88 light years from us. It's a binary also, as many stars are, 2 white main sequence dwarfs. The period of these binaries, as far as their revolution around each other from their center of gravity, is 87, just a little bit over 87 years. And going back to, similarly for Razelhig, that was basically an 8-year cycle going around. It's the companion going around the main star. The third star is going to be Zeta Ophiuchi. It's 2.6, blue main sequence, 366 light years, radius 8 times our sun. You'll notice, and I'm not going to go through reading all these, you can see the symbol for the sun, and I'll speak about, the mass, the luminosity, and the radius, comparing it to our sun, which is, a nice, easy comparison for a lot of these objects until they get into some of the extremes. And I'll just call out some of the unique characteristics. For instance, in the case of Zeta Ophiuchi, it has a radial rotational velocity of 400 kilometers per second, which is kind of high as a lot of these stars go, thereby lending itself to be classified as a beta Cepheid variable. This is primarily variations from surface pulsation, which may have a little bit, which, I don't want to say correlates, but does may have some relationship with its higher rotational velocity than most stars. Within the next few million years, and so, we talk about these ages in stellar terms. A few million years, of course, is not a very long time for us, living on this planet, it is. But as far as stellar or universal timeline, a few million years isn't very long, but it's expected to expand to a red supergiant. And this has sufficient size mass to go supernova, and then ultimately end up becoming a pulsar or a neutron star, not necessarily a black hole. Unlike our sun, which will go to supergiant, but it has insufficient mass to go supernova, and basically will lose all of its material and I think become a white dwarf in its end stages. Okay, another prominent star you had prior. This is Delta Ophiuchi, red giant. You can see all the factors associated with it as far as mass, size. It's an optical double with another star, and these stars both sit over in. Golly, lost my cursor, and I lost where the star was. Not down there. Oh well, sorry, I just don't remember where it is in the constellation. Doug, you know where this one is?
Where? What?
You had Delta. Oh, wait a minute. Is that Delta? Yeah, I think it's right here. You had prior.
It's in the middle there.
Yeah. Okay. So that was it that I hit on real quick there. So and those are, basically are two stars that form the left hand of the serpent bear. So they're off. You're in the middle, off to the left a little bit. Okay. Some other notable stars. Sabauri, Belto for you guys, an orange giant. It's fairly large compared to our sun. Kappa Ophiuchi, another orange giant. This is somewhat common in a lot of the stars that are in Ophiuchus as far as being giants. Of course, there makes sense. They're some of the more prominent stars. Theta Ophiuchi, which is down near the bottom of the. I had it earlier. There it is, right here, which forms a little bit of one of the feet of the figure. There's some interesting stars down there too. And then that is also a beta Cepheid variable. Sinistra and new Ophiuchi, an orange giant. And this is an orbiting brown dwarf, and these are some recent discoveries over the past couple of decades was found orbiting this one. It's still about 151 light years, so I imagine a little bit difficult uh, to to try to spec that out. But you can get a little bit of an idea. The figure there, this brown dwarf is that figure 21.9. That's Jupiter, so it's mass-wise, it's about 22 times the mass of Jupiter. It has an orbital period of 536 days. And then a second brown dwarf was also discovered 6 years prior in 2010. Its mass, a little bit more than the other one, a little bit more, almost 25 Jupiters. And it has an orbital period of 3,169 days. So that's kind of an interesting star. That's a nice little multiple system. These are some other notable stars, and I'm not going to go through all of them. I think Marfic is kind of an interesting one up the right side, as far as being able to spec out some of the other things in the constellation. And the only other one I really want to talk a little bit about is Barnard stars. This is a star that's relatively close to us. It's only just under 6 light years away. The apparent magnitude is a little under 10. So as far as most telescopes, it's probably going to require at least a 6, most assuredly an 8 inch, and it can be seen. And one of the unique things about this particular star is it has one of the highest um, uh,
Proper motion.
what's that?
Proper motion.
Yes, proper motions, which is relative to our solar system, and it's 10.3 arc seconds per year, which especially under an 8 inch and anything larger, it's very very discernible. Except it takes a while. Typically, you won't see anything like this in double digits or even approaching it. Most of them are going to lie down in the low single digits. But it's a star that's 7 to 10 billion years old. It's a flare star, a solar flare, which means it'll flare up every once in a while. But one of the interesting thing about Barnard's, it's in one of the Astronomical League's programs. Can't remember which one, but it was kind of interesting. I actually, you know, watched this one for a year. Made one observation, went back 6 months later, thought I could see a little motion. But then when I went back, finally after the year, there was some discernible motion. It's rather difficult because the surrounding field stars are not any brighter, so it's very difficult to compare to other stars. And so therein lies the difficulty of being able to track this thing. So a good accurate diagram really helps out. But it is kind of interesting over the pace, over the time of a year to actually see this kind of a movement in a star field. Deep sky objects. As you can see, there are a lot of Messier objects. And you will notice, and I'm not going to go through all these either, but you can see I have a couple of examples. M9 is up there in the upper right as far as some of these pictures. M10 below it to the left, M19 off to the right, and 107 lower right. And you can notice what type are they? They're all globular clusters. All the Messier objects in Ophiuchus are globular clusters. And you can see the data on there. The first number is the apparent magnitude. The second number is going to be the distance, of course, in light years from our solar system or Earth. And then when they were discovered, of course, most of them were discovered by Messier or subsequently confirmed by some other astronomers. You'll notice M107 was really discovered a little bit later and not confirmed until the 20th century. But like I say, they're all globular clusters. Uh, One of the thing, and here again, the Astronomical League has a observational program on globular clusters. And one of the things besides, trying to look at, I think they list a little over 100 clusters and require 75 to be diagrammed and described. To most extent, you look at a globular cluster and one looks like the other, but there are actually some variations in how high or dense the central concentration is. Strong inner cores, intermediate, rich, intermediate, mild, intermediate, loose concentrations. Rather loosely concentrated or loose towards the center, loose, very loose, or almost no concentration towards the center. And a lot of these focus on the center parts of these clusters. And as far as being able to look at the differences, for the most part, I take a look at M19 and M10, very, very similar with respect to especially their centers. Whereas you take a look at M9 and 107, there's some significant differences there and significant differences between the two. But you get a good idea of some of these different classes of globular clusters. And certainly Ophiuchus is rife with them, but that's the end of those. Moving on to some other deep sky objects. Interesting one, Kepler supernova, remnant first discovered in October 1604 by Johannes Kepler. He observed it for a year. Had a apparent magnitude of -2.25 to -2.5, and at that time could be seen by the unaided eye at night. NGC 6355, surprise, surprise, another globular cluster. But it's kind of neat. This was one that was discovered by Herschel in '84. Fairly good size, 4.2 arc minutes. A little dim though, so it'll probably require at least a 6, probably working up towards an 8-inch telescope to pick up. Or if you have a sea star, I would imagine it's a very easy object after 30 minutes to image. NGC 6240 Starfish Galaxy. It sort of looks like a starfish a little bit. Um, it's an ultra-luminous infrared galaxy. 12.8 is the apparent magnitude, 400 million light years away. That's why we don't get the benefit of that ultraluminosity. Highly irregular, likely remnant of two colliding galaxies. And you see, it's kind of unique looking. This one with the core and with the material, some of the dust lanes in it. I can see very easily where it might have been a result of a collision because there's a lot of irregularity, very little uniformity, well, no uniformity really in this particular galaxy. And then we have Barnard 68, which I thought was kind of interesting. You look at it first, you may think it's a void, but the fact is it's a dense molecular cloud, dark absorption nebula. It's only about 500 light years away, and the size of the area, as far as the radius, and I'm going to take it across the middle, is about a quarter of a light year, and believed to be mostly molecular gas and dust. And then finally, oh no, we've got a couple more here. So we've got, and I thought these were just some interesting deep sky objects. 6572, the Emerald Nebula, very young planetary nebula, 8.1. So well within the range of most amateur telescopes, but it's got a unique look, of course. Here again, difference between looking at it observationally and then imaging it is probably going to be tremendous. I doubt with most telescopes observing without imaging, you're going to pick up all that nebulosity, especially to the upper and lower extremes of this particular object. Little ghost nebula, kind of interesting. Here again, a planetary nebula that has a central white dwarf, which is very easy to make out, and you can see all the nebula material moving out from the center of that. The Twin Jet Nebula, kind of interesting object, interesting looking planetary nebula. Here again, if you were to look at it through the telescope, you're probably only going to see the central star. I doubt you're going to see most of that material off to the left and right as far as what looks like. It makes it look like a butterfly. Other than the fact that it might need to be imaged in order to be able to draw that out. And then finally, Ophiuchus cloud complex, kind of interesting looking interstellar cloud complex, about 460 light years away. The reason I bring this one up of particular note, it's one of the closest star forming regions to our solar system, to Earth. I don't know how much study this thing has garnered over the years, but certainly being this close, I would imagine it probably has, especially with respect to cosmology and star formation. So that's it in a nutshell. There are the references I used, as usual. The Herbst-Russell diagram for your reference. And thank you for your attention. Are there any questions?
I think I saw one on the chat.
Oh, I got to get that back up. Let's see if I can get la-di-da. There we go. Okay. Just had to get rid of. Oh wow. Okay. Oh, still stickers available. So the entire constellation can only be seen between the entire constellation. Actually, I think it was plus 80. A little bit, Doug. I think a little bit
No,
bigger. No.
because it goes all the way down to minus 30.
Oh, okay.
So you'd
Oh
have to
no.
be the
Yeah,
entire
you're right. Okay.
constellation.
Yeah.
That's as far north as you could go.
Yeah. Okay. Matthew, yeah, as far as being able to see 6240 looking like a starfish to the visual observer, I would think probably not, because you're just not going to be able to pull in all that added material through the eyepiece. How much imaging it would take. Certainly, I would imagine if you put this to regular imaging or hit it with a C star, it's going to draw out a lot of that. You'll see that. So yeah, I don't think you're going to get that at the eyepiece. Anything else? Okay, thank you, folks. Let's see. I've got to go in. What does I have to do, Stephen, is figure out. Oh, here we go. Host tools, enable participants, advanced. Stephen, just trying to figure out how to make you a host.
Are you the primary host?
Yes.
Okay. Go up to the little box on the right-hand side of my picture, which has everything in it where the three dots are.
Oh, yeah, yeah, yeah. Thank you. Okay. You
Let's
are
see if that'll
co-host, sir.
work. Okay, I'm going to share my screen. Um, and let's go share that one. Okay. And I have no idea why that came up. We're going to figure this out. All right. So, as I said, first of all, I'm Stephen Ferris. I don't come to these very often anymore because I have a lot of different things going on Thursday nights. But it is good to be here again. I used to be a little bit more frequent contributor I came in to do this one because Connor was looking for someone to fill in for him while he was out. I'm also the director out at Timpa. If any of you have been out there, I think I've met a few of you. Always encourage people to come out and join us. We'll be out there tomorrow night and probably Saturday too, if anybody has some time and wants to make a not so long trip out to the desert. As I was saying it before we started, half of this presentation is basically copied directly off of the presentation that Doug gives during the class. The other half is stuff that I put together on my own. So if some of this stuff looks incredibly familiar, it is because I just stole it from Doug. The other stuff is going to be stuff that's going to be focused a little bit more on the photography side, because filters are a very important part of photography and astrophotography as well. So, what is a filter? It basically is something that is used to reject certain signals. And in this case, is mostly used to reject certain wavelengths of light. Visual filters are usually used to enhance four different types of objects. The most common are going to be colored filters, which are used for planets. Also, there's nebula reduction, which are used for broadband, narrowband, and light pollution. We'll talk a little bit more about that. There's moon filters, which are neutral density and polarizing filters, and there's also sun filters. And why use filters? Well, in the case of the sun, you have to. You'll burn your retinas out if you don't have a filter. In the case of the moon, you're using it to get a little bit more detail on the moon and also take out some of the glare. But for other objects, it basically clears out some of the extraneous light. So there are filters which, to various degrees of success, are able to work out some of the extraneous light that comes from things like light pollution or the moon. And in other cases with planets, it tends to highlight certain features or details by cutting out extraneous light that we're not looking for on planets. So the top two are going to show you what it looks like. The Orion Nebula, I believe, through an O2 filter, or an O3 filter, and then the bottom two are with what you have a red filter on Mars. So you can see a little bit more detail if you're doing things visually. Other applications with colored filters are to enhance surface features of the moon and the planets. There are several different visual filters. I usually think of these color filters as being primarily for planets and sometimes the moon. They're not really, there are a couple which have a minimal effect on deep sky objects, but there are ones that have better effects. Yes, Doug.
No, I'm just showing. Here's a
Oh,
yellow one.
yeah, there's a yellow filter. So there's several. What happens is that there's many different colors. There's also a common numbering system, which is universal across all manufacturers. And there's light yellow, yellow green, straight up yellow, and dark yellow. And I'll go through the colors first before we talk a little bit about why use a brighter and why use a lighter, or why use a darker filter. That's a darker yellow. Is that a number
That's a
12?
15.
That's a 15. Okay. So that's a dark yellow filter. There's also orange and red filters. Orange is a good one for Mars and for Jupiter's belts. Red is a good one if you're trying to find any features on Mercury. You're going to need some kind of a red filter. It can also pull out some of the belts and moon transits on Jupiter and show some detail on Saturn. Dark red can be useful for certain planet sky contrast in the terminator of the moon, and also the polar caps on Mars. And green
That's
filters are good for
25. Red.
and and the green filters are good for the moon details and the polar caps on Mars, and a dark green is similar. It also shows some details on Saturn. And blue filters are actually one of my personal favorites. With a light blue filter, it tends to bring out some low contrast features in a lot of different objects like planets. Good one to have for Jupiter as well. I love a light blue filter with Jupiter because it brings out a little bit more of the contrast between the belts and the zones. Dark blue can bring out some of the dust storms on Mars and some of the belts on Saturn. And then blue can be for feature contrast And there's also a violet, which can help bring out perhaps a little bit of detail on Venus, and also the polar caps and some of the details in Saturn's rings. Now you'll notice that there's a distinction between the I'll go back one step real quick between the light blues and the dark blues and the light yellows and the dark yellows. Each one has a specific use. It's good to have, if you're going to use visual filters for planets, to have a number of these in different hues and different levels of brightness. As a rule of thumb, in the past, I've heard that if you have a large telescope with a large light throughput, it's more forgiving with the dark colors filters than with a smaller scope would be. But that varies from telescope to telescope and design. But as a general rule, if you're going to use very dark colors, you probably want to have a lot of light coming throughput, which means a fairly big telescope. So when I use a little scope ranging from 5 to 8 inches, I tend to lean more towards the lighter colors because too much light taken out can be a little bit distracting, makes it hard to see what you're looking at. There are also visually, and we'll come back to this subject as well, broadband versus narrowband filters. So the basic principle of any filter is it allows certain wavelengths of light to be transmitted and not others. Broadband filters will emit or will transmit several different frequencies or a wide band of frequencies, whereas narrow bands are very, very focused on a single frequency or around a certain frequency of light. Now, it's not perfect. It's not like even the narrow bands are seeing only one frequency, but you'll notice that within the diagram here, there are some bands which are a little bit wider, a little bit others which are a little bit more narrow. And basically, the reason we use narrowband filters visually is that we are looking at things which are emitting in very specific spectra. So, for example, the gases in a nebula are very, very fine. They're very low pressure. They're very are rarefied compared to anything on Earth, and as a result, when they fluoresce, they reflect. They basically emit light in very specific wavelengths, depending on which type of gas being is being excited at that time, and then re-releasing photons as the electrons drop in orbit. And we can produce filters that are designed for very specific, very common gases. In these cases, they're more plasmas, but we won't get into the details of that. Basically, what we're looking at in these cases, instead of a wideband filters that we use with the nebula, are filters that are basically focused on very specific wavelengths that are produced by hydrogen alpha lines and also by hydrogen beta lines, and most importantly for visually oxygen 3 lines. Now, I don't want to go into too much detail about what those specifically mean. Hydrogen alpha kind of speaks for itself. It's the first line of hydrogen. O3 is oxygen, and hydrogen beta is another line of hydrogen. We usually focus on the hydrogen alpha and the O3 filters when we're doing things visually. There's also others which are light pollution reduction filters. In the past, when cities were doing lighting based more on things like sodium vapor and high pressure, well, it was sodium vapor, they switched from high pressure mercury. But the light that was being put out by cities was emitted in a specific spectrum, and astronomers, both professional and amateurs, could create filters that would basically filter those out. And so there are a lot of really good filters out there for removing light pollution. The problem is and Doug's got one there that's a good light pollution filter. And we sometimes refer to them not interchangeably, but sometimes mistaken as nebula filters. But they're actually slightly different designs between a quote nebula filter and a light pollution filter. The point being that when cities switched over to not charge coupled, but to what's the word I'm looking for? Switch over to LEDs. they started emitting in multiple spectrums again. And so it became a little bit harder to produce a filter that was specifically good at removing the light. Um, Broadband filters, again, are going to be looking at um, are good for things that like use that are not emitting in specific spectra. So things like starlight, or it can be useful sometimes in light polluted skies, but it just depends on the situation. But narrowband filters are very good at looking at very specific wavelengths emitted by diffuse emitters. And so they're the ones that we use mostly visually are going to be oxygen 3. And we'll talk about why that is as well, but you can also use the hydrogen alpha or the hydrogen beta lines as well. And there are specific filters for that. And we'll come back to this a little bit later when we talk about photography and the like, because there tends to be choices which are made based on it as well. But visually, when we talk about an O3 filter, which is the one I use most often on the big telescopes looking at a nebula, we're talking about one that specifically filters out all light except for that emitted by the oxygen atoms, or the oxygen atoms emitting at the third level. But oxygen 3 and hydrogen beta are other two common types of narrowband filters. And the hydrogen oxygen 3 is great for things like the Veil Nebula, or the Ring Nebula, Dumbbell, the Orion Nebula, Lagoon, or all show up a little bit better through an oxygen 3. It tends to remove some of the light pollution, a little bit of the air glow, and some of the other things that tend to obscure some of the details in the object. It also gives things a very bluish cast because it is emitting in that kind of wavelength close to the blue. Hydrogen alpha and hydrogen beta are very narrow band. Hydrogen beta is at the 486 nanometer line, and it's good for the Horsehead, the Cocoon, and the California Nebula, but it's best under dark skies with large apertures, and it's only useful for a few objects. Also, so the top one is what an oxygen 3 looks like in real life. They kind of have a bluish purplish tint, but they kind of have a gossamer effect in the red light. The images show on the right what it can do for something like the Orion Nebula, wash out, take out some of the background light there, the extraneous light that we don't want. It is just very effective again for things like emission nebulas and planetary nebulas. Where it tends to not be as effective, of course, is with things that are broadband emitters like stars. Well, galaxies are mostly the lightest stars. Some of it is coming from nebulas. But in this case, it shows that these kinds of filters can be used to some effect with things like galaxies, but they're not as effective as they are with nebula. And then also another type of filter that's very common for moon viewers, those of us who do that, are moon filters. And moon filters are a real nice trick, especially if you have a very large telescope like the 16 or the 14. You do not want to be looking at the moon. And Doug's got one right there. Is that a variable polarizer?
Well, this is a regular moon filter, and
Neutral
it
density?
takes out 87%.
Right. So if you're looking,
13% filter.
so when you're looking at the moon, you don't necessarily, with a big telescope, you don't necessarily need more light. What you're looking with, the real advantage the telescope does is you can crank up the power with it and see the details. But if you're just adding more light, it's going to get really intense to look at. So it also increases the contrast to use a filter. There are two types, which are variable polarizers. There are actually two polarized filters attached to each other. You can sort of dial in how dark you want it to get. And there's
Yeah,
also the
see,
neutral
watch.
densities.
This is the variable polarizer.
Yeah, you just rotate one side and it gives
It's
you
dark,
a
it's light.
yeah. And then the neutral density filters are good if you want a set level of darkness. Something like an 83% would be great for something like the 14 or the 16 because it's removing most of the light and most of the glare. And the other thing with the big scope is it's not always comfortable to look at the moon even in narrow phases, so it's good to have some kind of a filter. Now for the sun, and I'm going to go through this relatively briefly because I'm not a huge fan of sun filters. Some people love them, and I'm not criticizing them. I've never been, I've destroyed some equipment with them, and I'm not a huge fan of something where you're actually looking at the sun unless it's a hydrogen alpha, which is usually pretty safe. Now, these are safe, but you just have to be careful in how you use them. There are two basic kinds. There's the Mylar film, which are usually white light filters. They're available from a number of vendors and can even be homemade. We used to have a workshop that made these. I think we ran out of Mylar material. We can always talk to Connor to see if he ever wants to get us some more. But the other type is glass, which has the filtering material enclosed on the glass. So I believe Doug has is that a glass one?
Glass one.
Okay. And that's what, 10 inches?
It's 10 inches and it's damaged.
And it's damaged. You do not want to use a damaged filter of any type with the sun because even a little bit of emissions through it can damage your eyes
I
and
wanted
damage a
to
camera.
If you hold this one up to
comment.
the light, you'll see pinholes where the
Yeah.
coating is broken.
All right, I've been using the Botter Astro Solar safety film for, well, gosh, since 1988 when it first came out. I wanted to say that it's just not ordinary aluminized mylar.
Hmm.
It's specially coated. You can't just take a space blanket and make a solar filter out of it.
Yeah.
It's just a warning. You don't mess
Yeah.
around.
And that's an outstanding point. Make sure anything you're using is specifically designed as a solar filter. You don't want to just take random things like aluminized mylar and use that because it does not subtract out everything that you need to subtract to be able to do the sun safely, either visually or for cameras.
Don't use a space blanket.
Yeah, don't use a space blanket. That's not designed for this, and you can damage your eyes really badly with that.
You
I
can
tell
Google
people,
for it.
I always tell people in my classes and whenever they are asking me about solar filters, I say one thing for sure. If you have a full aperture solar filter, um, every time you use it, you check it for
Very good.
damage.
Yes.
You just put it up to the light and see if you see pinholes of
Anything.
light coming through it, because that means it's bad.
Yeah. So white light filters also have some of them are not literally white light in the sense that they produce an orange image that is usually the glass filters. It's a more true color of the sun. Thousand Oaks makes some very nice ones. They are, however, a little bit more expensive than a similar apertured Mylar one. I have one of these. I haven't used it in years, but it was at its time a very nice solar filter. You can see the 8-inch Schmidt below and a Max Suit both with solar filters. These become very popular around eclipses and things like that. But they tend to produce a nicer orange image and are a little bit better quality than what you get with the Mylar. But the Mylar works just fine too, as long as you're careful with it. There's nothing wrong with that.
They give
Some
a
other thing.
bluish, whitish image.
Say again.
The Mylar filters give you a kind of a blue-white.
Yes, it gives sort of a blue-white, whereas the glasses and filters tend to produce sort of an orange yellow image. Few warnings with that. Please, please, please never use the sun with a telescope with without an undamaged full aperture filter. Don't use Herschel wedges and do not use eyepiece filters. Eyepiece filters were once popular with very low-end telescopes purchased from things like the local grocery store or CVS or whatever was popular in those days. They melt. And not only even before they melt, they don't have proper filtering, and then they melt. And there have been several reported cases of people having eye damage from those things. Always inspect your solar filter for damage before using it. Don't stretch the Mylar film. Don't touch the filter surface, and don't let anybody else touch it. The oils on your skin can do things to it. Always handle the filter, handled by the filter cell. always store in a protective case and keep your finder covered. You don't want people accidentally looking through it and damaging their eyes. Even something as small as a finder can do a lot of damage to the eyes.
Also, the finder, if you've got a crosshair finder, if you don't keep it covered, you can burn out your crosshairs.
That's true. You can also burn out the crosshairs. And one of the things is unfiltered telescopes, the sun, shunning the sun through it can also damage the optics just in general. So you have to be kind of careful with that. Uh,
Normally,
you can make a Botter filter for your finder scope too, you know. I've
yes.
done
yeah,
that.
Um, Normally, with something like just a standard Newtonian reflector, it's okay to point it directly at the sun and you can do a projection with it and you're not going
yeah,
to hurt it. The problem with most other telescopes like refractors and Schmitz and
it's the
much stuff
glass.
is they're a sealed system. The air
Yes,
inside gets hot really
yes,
fast, and that's
yeah,
how you damage the scope.
yeah, yeah. So if with any scope is you need to be doing some kind of filtering. Projections can work, but the risk there, of course, is somebody who doesn't know what they're doing, like a kid. If you're doing
Stick
this with
their
a group
hand
who
in
come
front of it.
along, puts their hand or decides to get cute and put some paper in there, it can, see if they can set something on fire. You just want to be careful. It doesn't happen often, but if you're dealing with a group, you always want to have a controlled situation with solar.
I used to actually demonstrate that with a 6-inch
Yeah,
Newtonian. I would light a
yeah.
piece of paper on
You can,
fire.
you can do some damage with them. The other type of um, solar filters was called the hydrogen alpha. So it's also looking at that hydrogen alpha line coming, but specifically from the sun. And it converts a normal amateur astronomy sized telescope into an H alpha type of solar telescope. Um, and there are several manufacturers. Well, there were two major ones. I think one of them is pretty much out of business. Coronado used to make
Yeah,
these very nice ones. They were bought up by Mead at some point. Mead was bought by Orion, and then they all went out of business. The other one is Lunt, which is still in business and makes most of its products here in Tucson. They have some very nice, very, very nice hydrogen alpha telescopes, usually 2 to 4 inches, but it provides more than enough light for a good image. I looked through some of these; they are beautiful instruments. If you're willing to spend $2, 3, $4,000 on a sun scope, and they can only be used with the sun, they filter out so much light that you can't use them with anything else. And more importantly, you do not want to disassemble one of these things because that would potentially ruin the optics and the safety levels that these things provide. The hydrogen,
Blunt is a 40 millimeter hydrogen alpha scope that's very economical and it can be
yeah,
used to take images. And you can
yes,
double stack it.
yes,
That's what I own.
yeah, and they're beautiful instruments. They're beautiful what they can do because they'll bring out prominences and some along the edge you can see some of the loops and the like and
Yeah.
they're beautiful
It
and you can also
shows the
right,
chromosphere, basically.
shows the chromosphere. Yes, it
Yeah.
shows the chromosphere rather than the photosphere, so you can see a lot more features than just sunspots. In fact, if you're looking for sunspots, you might do better in white light, but
you would.
if you're looking for all the other details, you're doing better in the photosphere. I'm sorry, with the hydrogen alpha, but hydrogen alpha is if you're doing solar imaging is really ideal. It's a beautiful way to look at things. The difference, of course, is that it can be a little bit more expensive for some of the higher end ones than with a conventional just white filter over a telescope. So, some recommendations for basic filters would be, if you're just looking to get started, red, blue, yellow, and then some kind of a lunar filter, either neutral density or a variable polarizer, and then a white light solar filter of some kind that can, if you want to do that. But if you have a small aperture, go with lighter shades, and if you plan on observing the sun, make sure that you're using the proper materials and the proper equipment with that because you don't want to endanger yourself or others with the solar stuff. to my knowledge, no one has ever been injured while looking at the moon through a telescope. I've done it with a 60-inch telescope on Mount Bigelow. It is uncomfortable, but you will not go blind. But the sun is a very, very different beast. So just be careful with that. Okay, so my contribution to this, first of all, thank you, Doug, for all the material. My contribution is using filters for astrophotography. So I will try and get to this relatively quickly as we are getting late in the evening. But astrophotography generally has different needs than visual use. And I need to point out that I am not yet an expert in using filters for astrophotography. I did have to kind of do a little bit of research on this. And I'm sure there are a lot of details that I'm missing. And this is a very 30,000 feet kind of look at how filters are used in that. But the filter types generally fall in the two same categories, broadband filters and narrowband filters. And the objective here is not to make the image clearer to the eye, but to select certain wavebands that one wants to image. So some old school filters we've already talked about. Traditional astrophotography was done using luminance and broadband filters, usually as luminance, red, green, and blue, which are the traditional colors for creating a color image. In the days of film and CCD imaging, this was most of the common form of imaging that was done with filters. However, with the rise of narrowband filters, imaging was taking in a new direction. And narrowband filters select out the light emitted at very specific wavelengths, usually wavelengths that were very specific to where ionized gas is glowing. And narrowband filters were used by professionals for years, but it really took off in the public's attention because of images that were being produced by the Hubble Space Telescope, which for scientific purposes was looking at things through narrow bands, but also used that particular feature to create a lot of very publicly available pretty pictures. So the narrowband filters usually used in conventional images that we see with Hubble, if it's in the visual spectrum, are through hydrogen alpha, oxygen 3, and sulfur 2. And then the Hubble palette was created using images that were originally black and white and taken through narrowband filters. And the image from each filter is assigned a color very roughly corresponding to its appearance. In fact, they really exaggerated things quite a bit. But the resulting image isn't exactly false color, but is highly amplified in order to maximize attractiveness. And of course, if you're a scientist, it has value too, because it can show you where different types of gases or plasmas are in different these kinds of objects. And today, amateurs can do roughly the same thing with very similar filters. So this is an idea of what the Hubble palette looks like. This is, of course, the Crab Nebula taken by Hubble in those three wave bands. Again, sulfur, oxygen, and hydrogen. I do not specifically at this moment remember which color is assigned to which. I believe orange is hydrogen, green is sulfur, and bluish is oxygen, but I could be completely wrong. Also, there's also nitrogen filters and others ones in there, and didn't look it up. But basically, I just want to give an impression of what this looks like when Hubble did it. With modern narrowband imaging, you usually do this with a monochrome camera. You typically, when you're using a color camera, you're just using the native color capabilities of the camera itself. Now, the color cameras actually do have filters built in to create the color capability. They're just so small they fit over the individual pixels in the camera, at least as I understand it. We won't worry too much about that. If you're going to do narrowband imaging with a camera today, you want to get a monochrome camera. What you're looking at there is the first one I could grab, which is one of the most popular out there right now. It's the ZWASI 2600, which has a very large imaging chip and is a monochrome camera. I think it goes for roughly $2,000 or $3,000, whether you get it firsthand or secondhand. There are cooled versions, which means that the chip is electronically cooled to reduce the noise factor. It's a very good camera, very popular right now, but that gives you an idea of what the camera would look like. In most filters can be attached one by one into a filter holder between the camera and the telescope. But most photographers are going to use an electronic filter wheel that can be controlled by a computer. And if you have the option of inserting traditional LRGB filters into the wheel, or luminance, hydrogen, alpha, oxygen, sulfur narrowband filters, the wheel doesn't care what kind of filter you put into it. This is a seven part. This is a wheel that contains 7 filters, and most modern filters are like that. So you can put all 7 types of filters and all 7 types of filtering systems on there, and you can now create images which have all 7 bands within them. Most photographic filters also come in 2 sizes. They're 1.25, but most of them are now in a 2-inch, essentially the same as visual filters, but they are put in these wheels and used photographically. There are some wide format cameras there's the 2 inches and the 1.25s that Doug has up. The wide format cameras, very wide format cameras require larger filters, and some very wide format filters are becoming available for top end wide field camera chips. Another one I just wanted to throw out there are dual band filters. If you're just starting out in photography and you don't want to go buy 7 very expensive filters and a filter wheel and all the rest of it, this is not a bad way to get started. Now, if you're going to go further into it, you're probably going to want to do a lot more than dual band filters. But if you're just getting going, this is a good place to go. I have a couple of these. They're becoming increasingly popular in sort of our introductory level of astrophotography. They are a filter that combine hydrogen alpha with O3 lines. And they're popular because they cut through most, not all, of the modern light pollution. The problem is they only work on certain types of objects, which are specifically, again, emission nebula. So this is an example of a ZWO 2-inch dual band filter that it would attach into an astronomical camera like the ones that ZWO produces. There's also a clip-in version for DSLRs if you have that kind of equipment available that also does the same thing. And of course, a shout out to our smart scope friends, of which I am one. Most smart scopes now have these built in, and this includes the C-Stars. And C-Stars will put dual band filters into place automatically when looking at certain types of objects. And that is the end of the presentation. Any questions, comments, thoughts on any of this? Anything I missed completely, blew up horribly, utterly destroyed?
Quick question for you, Stephen, about
Yeah.
I've got a C star as well,
Mhm.
primarily just on observing at night, but it does come with a sun filter. Do you know, has there been any issues with using the sun filter with the C star?
C-Star is, of course, you don't look through, so there's no risk to your
Right.
eye. In terms of the chip, I would take the same precautions with it that you would with a visual filter, and just put it not necessarily up against the sun, but against a bright light, and just look for any kind of holes or damage to it. Because if there is any damage to it, it could potentially damage your chip, which you don't want. So anything that is a precaution for the visual, you also want to take with purely photographic, because you don't want, the chip is photosensitive too. You don't want to destroy it with the UV and all the other stuff that's coming through the lens. One thing I would say is never take a photograph of the sun without the filter. It will destroy your chip very quickly that way. So that'd be one thing. Mine came with one too. I have not tried it, in part because I don't.
Is it
It
a
is.
glass filter, or
I'm pretty sure it's a glass filter.
right?
Yeah, it's a glass filter.
Okay.
Stephen, I use the S50 with the glass filter for this last solar eclipse, and it worked just fine.
It did work. Okay. Okay. My only thought with it is I don't want to take the whole thing out during the daytime in the heat of the sun, because I have destroyed cameras that way in the past. Now, hopefully the ones that are in the C-Star are a little bit more robust than that. But yes, many people use these things with the solar eclipses, and they were very successful with that. In fact, that was one of the things that really made the smart scopes very popular, was the eclipses, people taking them with them to go look at the eclipse, and they work beautifully for that.
Oh yeah, that's a good idea. I hadn't really connected that. the dots there with the solar eclipse. But yeah, that'll be great to see it through the
Yeah.
sea star.
Yeah.
Like he said, make sure you check your filter before you use it.
Always
Right.
check the filter because chips can be destroyed just as easily as retinas can.
Yeah. All right. Thanks, guys.
Yeah.
I got a couple questions for you.
Yeah.
Curious about kind of how they're made and how they work. First, a simple one. Polarizing used to be you had a piece of plastic that was smashed together between two pieces of glass. Do they still make them that way, or
Now,
no? Okay,
there are two separate glass things here, and you rotate. One is polarized in one direction, and the
gotcha.
other. And when you cross polarize them, gets dark because the polarizations are one is
Yeah,
this way, one is this way, and then when you line them up again, it becomes transparent.
right.
And they're twice as thick as a regular figure because it's two pieces instead of one, and they're connected together. I can't pull them apart, but I can rotate them like that.
Cool. Yeah, that's pretty cool.
They're not very expensive either. Just
Yeah. They're less than
$20,
$100.
$30 for a
Yeah.
2-inch.
So for how they're made, it sounds like most, at least good ones, are probably made of glass.
Yes.
Yes.
Is I asked this because I've seen pictures of like glass lenses or whatever that were colored. You know, when you looked at the picture, it looked, blue or green or something. And I'm wondering, see, because I was thinking most filters and things are made by depositing layers of, something that, responds to a particular frequency or whatever. You
I
deposit the
think
right
what they
layers,
do,
but what I guess my question is are they also making them where the glass itself is like doped to a particular?
I think that's how they make them now. They use um, these filters like the one I'm holding in my hand. This is a green one. It's made from optically flat glass, so it's optically flat on both sides, and it's very thin. I'm guessing it's only about maybe an less than an eighth of an inch thick, I would say, in terms of thickness of the glass. And they're made now, they take the glass and they make it with different metals in it. Like I know like cobalt, if
Mhm.
that put in the glass, it turns it blue. And so they use that, I think, to make the different shades. They use different ingredients in making the glass itself. And
Okay.
that's how they get the nice, pretty colors like that.
Yeah, my recollection is a long time ago, it was mostly just depositing films on the surface
Yeah,
of the
or
glass.
coatings.
Because that was,
Yeah.
I remember that when I was growing up in early astronomy,
Yeah.
that's how they made the filters because that was the cheap way to make them. You could buy the expensive filters that were made with the actual colored glass, but they cost a lot more. But nowadays, the colored glass filters like this one's like $10.
Yeah.
Yeah.
They
So
refined the process.
gotcha. Yeah. Yeah. That was kind of my guess. And on the subject of choosing the appropriate metal or whatever, I'm presuming that what we're looking at is atoms that have okay, this is a quantum mechanics sort of question. I presume we're looking at atoms that have electrons in certain energy levels that therefore absorb certain wavelengths of
I
light.
just don't know. I I only know what I know about the way they make these colored glass filters
Yeah,
because I actually was in Venice a few years back, and they make all kinds of glass in Venice. Venice is known for their crystal, and I got to tour some of their glass making factories, and they're
cool.
making all these different colored glasses, the red, the blue, the green. Not for astronomy filters, but you for whatever purpose, for regular glass. And it's like, okay, so now I understand how they make the colored glass. I don't know the quantum mechanics of why cobalt atoms in glass turns the filter blue. Not quite sure I understand that part.
Yeah, I think it has to do with the energy levels of the states that the electrons can be in certain energy levels. Different atoms have different values, therefore they absorb different wavelengths or different energy of the light. That's my best understanding at this point. I'm just trying to understand.
You're probably beyond me on that.
um, okay, another one for you. Since we live in a dark sky area, I'm wondering about filtering out light pollution. Um, have the filters also changed over the years, or do I need to buy a new filter if I have some, which I don't? But if do I need to buy a new filter? If my neighborhood puts in LED lights, and takes out sodium vapor or whatever, or are we like the band pass that allows a certain range of lights? We just filter out everything else anyway, so it really doesn't matter what your light pollution is. It's going to block anything else other than the narrow band that you're looking for.
I,
I'll see if I can take a stab at that one. I think the answer to that is if you're using the narrow bands, you're going to take out most of the light pollution, regardless of where you are.
Okay.
If you're using filters that were designed specifically to remove sodium vapor, they're probably worthless. But what I would check if you have, I would not discard anything, but just check it under different lighting conditions and see what works. I know for a fact with like an oxygen 3 or H alpha is going to do a pretty good job of removing 90% of the light pollution, whether you're under, Bortle scale 8 or Bortle scale 1. If you are looking at the older versions of like what used to be called light pollution filters, I would imagine it still filters out a fair amount,
they
but
do.
probably not as effectively.
If you just get what's called just a generic light pollution filter,
Yeah.
that does a pretty good job of wiping out most of the light pollution.
Yeah.
Okay? It's not narrow band. It's not just centered on like sodium or mercury.
Mhm.
It's a pretty
Yeah.
broad band light pollution filter. That'll still work probably
Yes.
just as good now as it did 20 years ago.
Okay, good.
In that
That
sense.
was
And
kind of what I was after.
you
Yeah.
can definitely find lots of those around.
Yeah.
Mhm.
I think that's what this one is. This one here is they just call it a sky glow filter.
Cool.
I think
Um,
that's just a generic light pollution filter.
So last question off the top of my head here. I hadn't really thought about it before, but you mentioned dual band towards the end there. I'm presuming again it's a case of they find the right metals or whatever that allow both band ranges, and we're probably not taking like two filters and putting one on top of another.
That's
Uh,
correct.
okay,
Yeah.
yeah, that's kind of what I figured. Okay,
I
cool.
mean,
Thanks. So that
actually,
was my list.
that one plot that Steve put up that showed the response for all those different filters at in the
It's
middle of
way, way back.
way back.
Yeah,
Yeah.
it's way, way back.
Um, actually, you could see a couple of the there was some dual band filters there. See if you can find it. They're not always labeled dual band, but if you look at their frequency response, you can see that they would work on two different bands.
Yeah, that's what I would do. Yeah. Cool. Thanks.
You can't find it, Stephen?
Oh, it's so far back, I don't think
Okay.
I'd be able to find
Don't
it.
worry about it. It's okay.
Are there any other questions for Stephen? Okay, hey Stephen, thanks a lot. That was a great
Yeah,
presentation. Really appreciate it.
of course.
I thought that was very fine. I'm going to go ahead and stop the recording here. You don't necessarily have to dive off yet. Anything else? Sorry.